Hi everyone, my name is Smitha, and today I'll be presenting our paper, Causal Inference Struggles with Agency on Online Platforms. Online platforms regularly conduct randomized experiments, also known as A/B tests, to understand how potential changes to their platform causally affect various outcomes of interest. However, experimentation on online platforms has been criticized for having, among other issues, a lack of meaningful oversight and user consent. At the same time, platforms are increasingly giving users greater control over their own experience on the platform, especially with regards to algorithmic personalization. For example, after a 6-year hiatus, this year Instagram brought back the option for users to view their feed chronologically rather than through an algorithmically filtered feed. For legal reasons, all large online platforms also provide the option to opt out of personalized ads. Often you can also toggle various other filters that control the quality, sensitivity, or toxicity of the content you see. The presence of such controls actually suggests an alternative to randomized experimentation. As platforms give users the ability to opt out of models, it becomes possible to run observational studies from user self-selection instead. For example, we may compare those who have a personalized feed to those who opted out of a personalized feed to determine the effect of personalization on the outcomes we're interested in. The use of observational studies is appealing as it may mitigate some of the issues with randomized experimentation, such as lack of consent. The question, of course, is how accurate would the causal estimates retrieved from such studies be? In order to measure the effectiveness of observational studies in this domain, we conduct 4 within-study comparisons at Twitter. In a within-study comparison, we analyze cases for which we have both a randomized experiment and an observational study. We then assess the effectiveness of the observational study by seeing how well it replicates the results of the randomized experiment. In all of our within-study comparisons, we start with a randomized experiment that has a control group and a treatment group. Users in the control group never receive treatment. However, users in the treatment group, although they receive treatment by default, can also opt out of treatment. We call those who actually receive treatment the treatment exposed group, signified as TE on the diagram, and those who opted out of treatment the treatment unexposed group, signified as TU on the diagram. For the observational study, we ignore the control group and only compare the treatment exposed and treatment unexposed group. We can then assess the effectiveness of the observational study by seeing how well it replicates the randomized experiment. As an example, let's revisit that case of estimating the effect of personalization on a timeline or feed. So first, we have an A/B test in which a control group of users only ever receives tweets chronologically. The treatment group, by default, receives personalized timeline. However, users in the treatment group can also opt out and switch to a chronological timeline. These users form the treatment unexposed group. The users in treatment who didn't opt out form the treatment exposed group. Now, I'll go over the 4 within-study comparisons that we ran. In the first study, we measured the effect of personalized timeline on the time that users spend in the timeline. In the second study, we measure the effect of personalized push notifications on the time that users spend on the platform. Notably, these push notifications are delivered from an algorithm. Many notifications on Twitter are simply as a direct result of some interaction on the platform. For example, a user retweeting your tweet or liking your tweet. Other notifications are often of the form, ABC just liked Z tweet, or X hasn't tweeted in a while. These are algorithmically delivered to you and don't directly involve an interaction between you and someone else. So here we're looking at how specifically these personalized push notifications affect user minutes on the platform. Similarly, in the third study, we measure the effect of personalized email notifications on the time users spend on the platform. And finally, in the last study, we look at Twitter's quality filter, which algorithmically filters out notifications that are low quality. We measured the effect that the quality filter has on the number of times a user blocks a stranger after being mentioned by them. By filtering out spammy mentions, we expect the quality filter to decrease blocks. If you think about what it means to block a stranger after being mentioned by them, typically this means that you notice the mention through a notification, and then you block the stranger because of that notification. So if the filter is working and filtering out these low quality, potentially low quality mentions, you would expect to have fewer blocks when the quality filter is on. We control for plausible confounding covariates that were available. For example, the number of tweets or followers that a user has, how old their account is, whether they are verified or not, etc. Now I'll present our results for these 4 cases. First, I'm showing the estimates from the randomized experiment. As expected, personalized timeline, personalized notifications, and email notifications all increase user activity on the platform. And the quality filter, also as expected, decreases the number of blocks. Next, as a baseline, the first observational estimate we test is the naive difference in group means estimator. Interestingly, the difference in group means says that the personalized timeline, push notifications, and email notifications all reduce activity on the platform. On the other hand, it overestimates the effect that the quality filter has on reducing blocks. And these are pretty significant gaps between the true estimate and the baseline, DIGM estimate. Next, we have the exact matching estimator, which exactly matches treatment exposed users to treatment unexposed users with the same covariates. And here we restrict to covariates that are discrete. So it does slightly, better on the first 3 cases, but still really missing the mark. Next, we look at regression adjustment, which estimates the counterfactual for each treatment exposed user using a regression function. Again, a little better, but still quite off. The direction of the sign is still wrong for the first 3 cases. And then lastly, we look at inverse probability of treatment weighing, which reweighs samples based on their propensity score, which we estimate by logistic regression. Again, similar story with this method. So overall, our results suggest that observational methods are a poor replacement to randomized experiments currently. In the first 3 cases, all 4 methods recovered the wrong sign of the causal estimate. And for the toxicity filter, the methods all overestimate the effect the quality filter has on reducing blocks. Furthermore, we believe that our findings are only a facet of a deeper tension between the success of causal inference and the motivations for user agency. The tension arises from the following. A major motivation for giving users greater control is that humans are complex, and we postulate that there is no model that can adequately model a user or their preferences. But observational causal inference typically requires exactly that. In most experimental paradigms, and in the ones focused on in our paper, observational methods need as an assumption some form of unconfoundedness or ignorability, and it'll be difficult to justify this assumption without the existence of an adequate model of the user. As an example, consider the setting in which we are interested in the effect that a treatment has on the amount of time a user spends on the platform. This is the outcome of interest in 3 out of 4 of our within-study comparisons. The slide illustrates a potential causal DAG for the setting. The user has a preference for a higher quality of experience on the platform, and their quality of experience is affected by the treatment. For example, suppose the treatment is personalized timeline. A personalized timeline may improve the quality of experience for some users and reduce it for others. Notably, when we give users the ability to opt out of treatment, then preference acts as a confounder. Users have a preference for having a greater quality of experience, and so, assuming some level of rationality, they are more likely to opt out of treatment if the treatment causes a worse experience. In turn, the better their experience, the more time they will spend on the platform. Therefore, preference acts as a confounder for the effect of treatment on the time spent on the platform. This brings us to our catch-22. A motivation for giving users greater control is to recognize that human choices are complex, and we lack a substantive understanding of what factors lead to which choices and outcomes on the platform. However, a successful observational study requires that we have accounted for all sources of confounding in most designs. Although not a formal contradiction, it seems unlikely that we can argue about the validity of an observational design without a better understanding of user behavior than is common in industry applications.